Hello everyone and welcome to PC Retro Tech. So in this week's video I'm going to be timing writing and reading to CGA memory. Now I'm going to be using a whole bunch of cards, some of which are here and others are in machines already, and that includes EGA cards and even an 8-bit VGA card. But the objective today is not to benchmark cards, because let's face it, when you buy a CGA card, they're so rare you basically just have to put up with whatever you can get. Instead, I've got a different question. If you were writing a demo or a game, what is the absolute maximum theoretical frame rate that you could get out of one of these cards? What are the things that are obstacles to getting that frame rate higher? And if you use an EGA card instead in CGA mode or a VGA card, would that make any difference? And what about if you switch machines to a faster machine? How much difference would that make? So the first thing I did is write a very short assembly language function called CGA draw fast1, which is going to fill in a block of screen memory with the same byte of data over and over again. Now, if you can understand just a couple of very simple things about this program, you'll understand everything today, because all the others are going to be minor modifications of this program. So in order to fill a block of screen memory, we first have to compute where in memory that is. So that requires two pieces of information, a segment register and an offset register. So the segment register is always set to CGA memory, which is always B800, and the offset is just where in that segment our block starts. So we compute those two things first, and I won't go into any details because they're not important. The main part of the program is actually this here, and it's repeated twice, once for the even lines and once for the odd lines. So it takes 8,000 bytes to fill in all of the even lines on the screen. So our first version of this program is actually just going to have a single block, and it's going to be the whole screen. So this is the important part of the code. It's going to repeat 8,000 times, storing the byte of data in AL into the segment offset that we computed. That's all there is to it. It's really simple. So the key is that we're going to be using the STOSB assembly language instruction to write bytes of data directly into screen memory. So if you understood that, then everything else today will be really straightforward. So let's see how fast this goes. Now I'm running our program here, and there'll be a little bit of flicker because the camera adjusts depending on the brightness of the colors. And what I'm doing is I'm running our program through 1600 times and changing the color every 100 frames, just so we can keep track of where it's up to. And then I'll get timings which I can use to compute the number of kilobytes per second that you can write to the CGA memory and the effective number of frames per second. But what I didn't tell you is I'm going to do this on multiple different kinds of hardware. So I'm going to use CGA, EGA and even 8-bit VGA cards which emulate CGA. And I'm going to do it on an original IBM PC and on a clone which can run at 4.77 and 8 MHz, and both of those will have an 8088 CPU in them. And I'm also going to run it on my Amstrad PC 1512, which has an 8086 processor running at 8 MHz. So we're going to get lots of information about how this writing to CGA memory performs on a variety of different hardware. So I've already run this through on my clone at 4.77 MHz, and I can already tell you it takes 86.4 seconds in total, and I compute about 18.5 frames per second and 297 kilobytes per second. So before I get into the graphics mode timings, I wanted to run a little experiment. What happens if you run our program in a text mode instead of a graphics mode? And initially you might think, well, it looks like we're getting 16 color graphics and we've tricked the card somehow, but that's not really what's happening here. It's a coincidence that the bytes that we're writing, the text characters, just end up being solid colors. And of course text mode can display 16 colors even on a CGA card. So I thought perhaps if I switch off the graphics mode and I'm just using a text mode, then I can fill up at least part of the CGA memory faster while it's not being accessed. But this seems to not be the case. In fact, this program actually takes 50% longer to run. And this was a bit of a surprise until I realized that I'm still writing 16 kilobytes of memory here. And text modes don't require 16 kilobytes of memory. So now you can see it's really a text mode. These are actually text characters. And it's only 80 by 40, and it really doesn't take very much memory for this at all. So if I just wrote the text characters, then this would actually run faster. So this is not a viable option. I guess the reason for this is that the hardware has to take some time to compute which pixels to display for the characters. In the next version of the program, I'm going to use the STOSW instruction instead. So this writes a word at a time, which is 2 bytes. So we only need to do this 4,000 times now. And basically it writes what's in the low part of the A register and the high part. And I'm just going to make those the same so that we get exactly the same result as before. So let's see how much faster this is. So here's what that looks like, and it is actually a little faster at 21.5 frames per second instead of 18.5. Now the difference comes down to the instructions themselves. The STOSB and STOSW both take 10 cycles per iteration of CPU time for each iteration. But of course the STOSW is getting twice as much work done. Now of course that's only counting CPU time. It takes almost 3 times as much if you count the bus accesses and the wait states on the CGA card. But anyway, the conclusion is that the STOSW with a wrap instruction is by far the fastest option at the moment. But it's pretty limiting. I mean, what if you want to draw a picture on the screen? With the wrap you can only write the same data over and over again. So I tried a few extra things. In particular, I tried using STOSWs just written out in a big long stream like this instead of using a wrap prefix. And this made things quite a bit slower, about 5 cycles per iteration slower than it was before. And this is because it takes 4 cycles to read the instruction in at each iteration. And without a wrap prefix, the STOSW instruction actually takes 1 cycle longer per iteration. So the other thing I tried was lots of different patterns here, switching STOSWs with STOSBs, and I tried every pattern up to length 5. But basically if you just add up the time for the B's and the W's, you get exactly what you would otherwise. So this didn't really make any difference. I did try turning the interrupts off, and I also tried inserting some no-ops between the even and odd parts, but none of this made any difference. So the best strategy really is just to use a wrap STOSW if you want to fill the screen with the same data, and otherwise to use STOSWs wherever you can. The next experiment was much more interesting. So I reasoned that these STOSW instructions, from the point of view of the CGA card, are not being issued at an optimal pace. So maybe we can take up some of the slack by putting in additional instructions between them. And I chose IncAX because at least that will do something useful. It's going to change the data value that we're writing into memory at each iteration. So we'll get some kind of pattern on the screen. And moreover, IncAX is only a 1 byte instruction, so it's really cheap to read in, only 4 cycles. And it only takes 2 cycles to execute. So I was actually right about this, and in fact some of the slack is taken up, and this IncAX actually executes in fewer cycles than you'd expect. So first of all, let's just have a look at the pattern that it generates. This is what the result looks like, and you can see it's much more interesting than just a solid color. Now that IncAX instruction, you'd normally expect if you put a whole bunch of those in a row that they would take 4 cycles each, taking into account the fact that the processor can do some prefetching. But you actually get the instruction for 2.3 cycles when you stick it between the STOSWs. And that really just comes down to the fact that the CGA card issues wait states some of the time to make the processor wait when you could be doing something useful. So let's try adding 2 IncAX instructions between, or 3, 4, 5 and so on, and see how the timings change. The results are quite amazing. You can see that if you just insert 1, 2 or 3 IncAX instructions, that the timings aren't too bad. But when you insert 4 or 5, you start to get back to the point where the pace that the STOSWs are being issued is wrong again, and so the timings really dramatically blow out. So for 5 IncAX instructions, that 5th one costs an additional 5.7 cycles, which is really quite high. And then, of course, things improve a little again and so on. And this will fluctuate up and down, just depending on how close you are to optimal timings. If you were writing a game or a demo, you'd probably want to do your computation in main memory and then copy everything over to the CGA memory. And that's exactly what the MOV-SW instruction does. It would just move a word of data between 2 addresses. Now, I'm not going to bother doing any computations in main memory. I'm just going to copy over whatever the contents are, and we'll just see a random pattern on the screen. But at least we'll be able to time how long this would take if that's what you were doing. This is what that looks like, and it just looks like you're scrolling a picture from right to left. And in fact, you can actually use code like this to do scrolling. So this is running at 15.5 frames per second. Which is pretty reasonable for a full screen scroll. The next thing that I tried was a MOV-SW loop which copies from main memory to main memory instead of to the CGA card. And I was really expecting this to be a lot faster, but it was only 40% faster at 21.9 frames per second. Now, something that really was slower was copying from CGA memory to CGA memory. This was almost twice as slow at 11.3 frames per second. So if you have to do a read and a write to the CGA memory, then that's going to be way slower than doing a read and a write to main memory. Now, of course, if you want to actually just copy data in main memory, if your motherboard supports it, you can just use a DMA transfer, and that'll be way faster. But at least this illustrates that you can't substitute a movement in CGA memory with a movement in main memory followed by movement to CGA memory. And that was something that I just didn't know before. Now we come to the fun part, all the promised timings, and of course I can't time absolutely everything we did on every machine with every card. So I've just picked out a few interesting ones here. And the first one is the rep STOSW, which is what you'd use if you were filling part of the screen with a solid color. And I've timed each of the different cards in my clone XT machine. And you can see that for most of the CGA and EGA cards you get exactly the same performance. But the EGA 1 to 800 Plus takes way longer. It's basically 50% longer. And the only reason I can think of that they would do this is so that CGA games would run at the right speed on an 8 MHz machine. So if you had turbo on, then performance would be about what you'd expect from your old CGA machine. The VGA card, the Singlabs ET3000, is actually just a little bit faster in CGA mode than a true CGA card. And that's not terribly unexpected, I guess. So the next one is STOSW, just repeated over and over. And this is the sort of thing that you'd have to do if you were doing some kind of effect where you had to do some computation in the CPU and just wanted to write the result directly into the CGA card. Of course, you'd put computations between the STOSWs. Now, the CGA cards, the true ones, actually perform a little bit better than the EGA cards here, which is a little bit of a surprise. One would have expected the EGA cards to give a little bit of a boost, but they really don't. Other than that, everything else is pretty much the same as we saw on the previous graph. The next one is the MOV-SW instruction, and this is what you'd use if you were doing your computations in main memory and then you just wanted to move the data into the CGA card. And you can see that the CGA and EGA cards are all about the same here, with the exception of the EGA Wonder, of course. But there are some minor differences between them, and they don't split between CGA and EGA this time. The unidentified EGA card is basically the same as the CGA card from IBM, whereas the Multitech CGA has a slightly different time. But otherwise the timing is very similar, and I should mention that the timings here are really reproducible, so you can rely on these down to the last digit that I'm actually giving in the values here. So now we've got the MOV SW, but this time we're just going from the CGA card to the CGA card, and you'd use this if you were moving a block of CGA memory about. For example, if you're doing full screen scrolling, or maybe just moving a picture from one part of the screen to the other. So this is a fairly rare case, and you can see that the CGA and EGA cards basically all have the same timings here, but the Multitech is just a little bit faster, but there's really not very much in it. Other than that, it's the same picture as we saw on the previous slide. So the other thing that I thought would be interesting would be to try the same graphics card in a bunch of different machines at different speeds. And of course, most of the CGA and EGA cards perform about the same, so I took just the IBM CGA graphics card, and I ran it in my IBM PC, the 5150, in my XT clone, which I've been using for most of this video, and then I turned the turbo on the XT clone so that it would run at 8 MHz instead of 4.77, and finally I ran it in my Amstrad PC 1512. Now the XT clone timings at 8 MHz is not terribly surprising. I turn turbo on, it runs about 50% faster, that's what you'd expect. But the Amstrad PC 1512 also runs at 8 MHz, and moreover, it has an 8086 CPU, not an 8088. And this can actually do 16-bit moves and bus accesses, whereas the 8088 has to break them up into two 8-bit moves or bus accesses. So this should be running way faster, and the only explanation here is that the CGA memory in this Amstrad is absolutely appallingly bad. And this is really not something that you feel when you use the machine, because it has an 8086 at 8 MHz. It really feels very zippy. But when you're just timing the CGA implementation itself, you can see it's really slow, basically twice as slow, more than twice as slow as an XT clone running at 8 MHz. That same picture is basically repeated for the STOSW, just repeated over and over. There's not really very much difference here. I probably should have mentioned that all of these timings for 1600 frames. It just is the way I worked out my benchmark, that I wanted to do 100 iterations, and I wanted to change to each of 16 different colors. And so this is why I chose 1600 frames for all of the benchmarks. Basically the same story again for the Move SW from main memory into CGA memory. 50% faster if you have the turbo switch on, unless you're using an Amstrad PC 1512. Here's the CGA to CGA timings. And it isn't quite a 50% improvement for the XT clone when the turbo switch is switched on here. The other thing that's kind of interesting is that the IBM PC is just a little bit faster than the XT clone in this case, and I can think of absolutely no reason for this, because this is CGA to CGA copy, and it's exactly the same CGA card running at the same frequency. I did time this multiple times just to make sure that this wasn't a mistake. So if you have an explanation for that, just drop it in the comments below. It'd be really interesting to hear your ideas on this. There's one last graph here, and this tells a completely different story. So this is main memory copy to main memory, and you can see that the IBM PC is just a little bit faster than the clone, but there's not very much in it. But when you switch the turbo on the clone, it goes more than twice as fast, and I really had to time this a few different times just to make sure I didn't make a mistake here, because you'd only expect a 50% speed up from the clock itself. So I really don't know why this is. Now the Amstrad timing isn't a surprise. Remember that it's been very, very slow for all the other graphs, but here the graphics implementation is out of the question. We're only looking at the CPU and memory speed here, and of course this is an 8086 CPU, and it's running at 8 megahertz. So we should expect it to be the fastest here, and indeed it is. So this really shows that if you're writing for the Amstrad PC1512, your strategy has to be completely different because a memory-to-memory copy is 7 times faster than a CGA to CGA copy. So that really changes the way that you've got to go about doing things, and it's something I had no idea about before I did this set of timings. So I found this really an interesting exercise, and it was quite enjoyable as well. I've been wondering about all of this for a very long time, so I hope that you enjoyed this as much as I did. I know that there's a lot of graphs and flickering screens, and not very many interesting graphics to look at here, but let's hope we can turn this information into some really good demos and games in the future. Anyway, thanks very much for watching. That's all I have for this weekend. If you liked the video, don't forget to give a like and subscribe, and we'll see you in a later video. Bye.